Oh, it is 2 questions. So that's the time of the.
So everybody knows there's a class going on here right now, so if you're not in the class, please either keep it down or move to the other side of the lab or something. The PIC lab's still open, but this room is reserved for class. All right, so we're looking at scikit-learn, right? How'd that go? Preparation? You guys ready for the quiz? Have you have any questions? Yeah.
Can you talk a bit about the support vector?
Sure. So the idea is that support vector machines are the idea of machine learning that says if we have, this is the traditional drawing, so I'm afraid I can't depict it much different from what you might have already seen. Okay? So let's say we have 2 features, right? These are the axes along, so 2 variables, right? x1, x2. These could be, what were the examples? Like petal lengths and what was the other thing in the, no, I think that it was the flower data set. What was that one called? The sepal length and,
Iris.
sorry?
Iris?
Iris, yeah, what was that data? There were several features in that. What were some of the features? You guys remember? Okay, I can make up. Okay, so there were a few different ways of measuring these different flowers, I think, and they were classifying which kind of flower it is based on these different characteristics. So x1 might be one of those measurements, x2 is a different measurement, maybe it had a 3rd dimension, etc. Okay? So it's a multi-dimensional thing, I'm only going to be able to depict it in 2 dimensions. And so you measure a flower, you measure its x1 variable, you measure x2 variables, these are called the features. And you get what's called a sample, right? And you plot where it is in space. And you measure a bunch of other flowers, we'll say the green flower, and they all kind of cluster around the same area, right? In this, what I'm showing is a 2D space, but could be multi-dimensional space. Then you measure your red flowers, all their variables in that same coordinate system, and you see where they lie. Okay, the idea of the support vector machine is that we're going to try to find some way to classify these 2 things. Obviously, we can't just say if x1 and x2 are exactly this point, then it's a red flower, because they're kind of clustered around here, right? And likewise, these are clustered. We can't just specify what point it is. So the idea is we can separate these with a plane. Let's say we draw a plane between them, or I say plane because I mean hyperplane. This could be a multi-dimensional space, but it's still kind of a flat surface. In 2 dimensions, it just becomes a line. We can separate them with a lot of different possible lines, right? At least our current observations. And we can say, if it's on, let's just use one line, for instance. Okay? Let's say we came up with this line. Look, it separates the 2 pieces kinds of data. Now, if we get a new measurement, it's a color that we don't know. Let's say we don't know what color this is. This is test data. This is all the training data. We fit our hyperplane to make sure we can classify the data. Now we're going to test it. Okay? So we get a new measurement, and it's somewhere over here. And we say it's on this side of the line. Therefore, it must actually be green. It must be a green flower because it was on that side of the line, on that side of the hyperplane. Now, if we get one on this side, then we say, okay, yeah, even though it's not around here, it's on this side of the hyperplane, so it must actually be a red flower. The idea of the support vector machine is don't just use any hyperplane that can separate the data, right? We're going to choose one that maximizes the separation between the data. And so one way that you can define it is if you can draw 2 hyperplanes that are parallel between the data, and you imagine that you spread them apart as far as you can, these 2 parallel hyperplanes, they're still parallel, spread them apart as far as you can, find the 2 parallel hyperplanes that you can spread apart as far as possible, then draw a hyperplane exactly in the middle of those 2, and we call that, this is the one the support vector machine chooses, because it maximizes the distance between these 2 sets of data. And so now we're pretty sure that if it lies on the upper side, then it's a green flower. If it lies on the other side, it must be a red flower. If you start adding actually blue flowers into the mix, let's say we add blue ones, let's say they're up here, and it works out nicely. Now, notice, remember, it's hard in 2 dimensions. If we had a blue flower, we're probably going to have multiple dimensions. So right now, I'm drawing them up here because by chance, we're lucky enough that in these 2 variables, they're all separable, but maybe that's not the case. Maybe when you look at this 3D space from the side or this 4-dimensional space from the side, they might actually look like they're on top of each other. But remember, in a multiple dimensional space, it might be easier to separate the groups than it is in 2 dimensions. Okay? So keep that in mind. Then what it's going to do is going to say, all right, I'm going to add the blue, and now I'm going to find the hyperplane that maximizes the separation between the blue and all the rest. And so what you keep on doing is when you're adding new samples or new target groups, then you want to find the hyperplane that separates the new thing from all the rest. And you end up with a bunch of hyperplanes by saying, all right, is it on this side? And if it's on this side of this plane, and if it's on this side of this plane, then you know it's green. If it's on this side of that plane, if it's on this side of this plane, then it must be red. And so you can kind of classify that way. That's how a support vector machine, which is binary by nature, it supports into 2 groups. If you use one separated from all the rest, and you make a series of decisions, then you can figure out which group it's in if it's multiple groups. Yeah.
Wait, so will each one, so in this example with 3, will each one have a hyperplane by itself that isolates it from all the rest?
That's
So
it.
will that create a region that
It has nothing in between. I'm not an expert in this. I never learned it as part of my, so I can't tell you right now. I was looking up a little bit before class, and I'm not sure if it's made on, I think it's all one big optimization problem.
Okay.
And if you do it as a linear problem, then there's a linear solution. And so I'm guessing that I'm not exactly sure. That's the basic idea. To be honest, all the simple references, all you really need to get is to get the picture of it.
Okay.
Yeah, I should look into that, and I'll provide you with a reference of that, yeah.
Just to clarify that, if we have 3 groups and we're doing a linear, let's say, classification, then would we get 2 lines, or would we just?
Yeah, so that's what I'm trying to say is, I probably shouldn't have delved into the realm of 3 groups right now. I should have stick to the usual, just the basic understanding of 2 groups. And you can imagine that if you can separate a certain class of data from all the rest, then you can do group classification as well. So I can't answer that question right now. Yeah.
In the prep, you said that certain classifiers are affected by the way that they're trained. Can you explain that by using this example?
I don't think that a linear classifier would.
Is it for multi-class classifiers?
But some of them can. I mean, just like the order in which you learn things affects how you learn, right? If I tell you one fact, you take that to be the truth, and then you get multiple somewhat conflicting ideas later on in life. You might think differently about things if you learn them in the opposite order. So what you learn as a kid, I mean, just trying to relate to humans and how we learn is maybe affected by the order in which we learn things. Does that sound plausible?
Yeah.
The same is true of some kinds of machine learning.
So they weight the first inputs more so than the
Potentially, but also if it's not, when you think about weights, think about like, you don't necessarily take in all the data and recompute based on all the data at once. It could be an iterative thing. It's only, once you have an average, right? Each additional thing that you add to the average has only a small effect on it. Now, it turns out it doesn't matter what order you take an average, it still works out. But if it was a nonlinear sort of average, then it's possible that later terms will if the order changes, then it will end up with a different result. So I can't give you an example of how that works, but you can kind of imagine that mathematically it could happen. I mean, I guess you just didn't have it. Well, you saw it because you're working on the fold tracks. the order in which certain operations were done, and the pseudo-random numbers, the threads, the order in which the threads operate on a variable could change the results. Yeah?
I was wondering if you could go over regularization, or like,
Regularization?
yeah, so it mentioned like the parameter and how like it would alter the margin or something.
Okay, I think that is a little beyond what we need to. Yeah, go. You had a question too?
Is it better to have poor resolution? Is it better for resolution?
You're saying, is it better to have poor resolution? So that's a great question. So he's saying, like, let's say we're trying to classify the image data set and, or the numbers, right? And so the numbers that you saw, who else asked the question? The numbers, the data that you saw, the numbers look very blurry, right? Because there was only like, I don't know, 8, 12 pixels, something like that, very few pixels. So it's a double-edged sword. It talks about the curse of dimensionality. As you increase the number of features, as you increase the number of dimensions that you have to classify things with, it takes more points, more samples, in order to figure out how to draw these hyperplanes, in order to fully train it. So that can be a problem. But on the other hand, if you have a lot of data, then more features is great, because then you can separate them based on in multiple dimensions. It's easier to separate things in more dimensions. So it's a double-edged sword. If you have a lot of data, more dimensions, great. It takes more time, but it will result in better classification. If you don't have very much data, then in order to make sure that things are trained appropriately at all, you need to maybe reduce the number of features that you have, the number of dimensions you're classifying. Yeah.
I like that generally like clustering and density estimation. Give an example like unsupervised learning.
When it's used. I think that it's sometimes used to figure, let's see. Does anybody else have an example from anything they're doing? You might have a better example than me. Yeah, cool.
I know if you have like a huge data set, you don't know like patterns of your customers and just feed it to the machine and figure out people who act this way, you should buy these products. So classify them. That would be actual.
Okay, so basically you know certain characteristics of people and you know the products that they're buying and separate them into groups. I'm sure I have examples. None are popping to the top of my head right now. I don't know why. Do you have one?
Yeah, you can use clustering to reduce the dimension of features by separating it into different color layers. And yeah, that's basically it. You have no idea about the feature, and you just like based on how colors are separated
Into a few different groups as opposed to that Yeah. It's used whenever you want to separate into groups, but you don't know what those groups are a priori. And I'm sorry that this is a really easy question, and I should have lots of examples. I haven't actually, but this is one thing, I haven't actually done research for anything on my own. Do you guys have examples? You're hearing all this. No? Davies? No? Okay, never mind. I saw you talking.
What are we good, find an example of that?
What?
What are we gonna find an example of?
K-means clustering. What's examples of clustering? Unsupervised learning. I should come back. I should give you some examples. So 2 things on my agenda are multi-class SVM and examples. And there's lots of very good ones of unsupervised learning. My brain's not working because I've heard lots. Sorry. Yeah.
There's a platform that you're training on random set example, and you can know that random choice. What are we supposed to pass in as a one-to array, but without like separating the targets to the sample?
So you're supposed to just pass in a 1D array into NumPy choice. Okay, so that was one way of doing it. So what that does is, so what were you supposed to pass in? Yeah, that's what you're asking?
Yeah.
Like indices of, because what you have, so that's one way of doing it. The other way of doing it was permutation, and then from the permutation taking the first end of those. So what you have initially is you've got your data. Each sample, right, each observation has a row, basically. It's kind of a, and each column is a different feature. So lots of different columns corresponding with features, you know, sepal length, I don't know, color frequency, etc. Of these different things for the flower, and then lots of different flowers, right? But for the flowers, I think they were all in order. So we had all the blue flowers data, and then we had all the red flowers data. Oops, no, that's not red. Then we had all red flowers data. So in our data matrix, we had 2 dimensions, right? Observations, samples, and then features. And so we wanted to pick a certain amount for training and certain ones for tests. So we wanted to randomly sample, say, n of them. All right, so there's 1, 2, 3, 4, 5, 6, 7, 8. I want to pick 5 for training, and then I'll reserve the last 3 for testing. And so what you're supposed to pass in the choice would be indices, 0, 1, 2, 3, 4, 5, 6, 7, up to 7, and it will choose randomly 5 of those. And that would correspond to, say, if it chooses, so like, let's see, 0, 1, 2, 3, 4, 5, 6, 7, you pass that array in, and you say, choice, give me 5, then it might come up with 0, 1, 3, 4, 6, oh, that's not very good, let's give it 6 and 7. And it'll return those things. And then you can say, all right, now select these indices out of my data, train off those, and test off the remaining ones. Does that make sense? The other way of doing it was with permutations, and I think that's the easier and maybe more efficient way. Is basically it says, I'm going to take this data and I'm going to shuffle it around, or I'm going to take this list and I'm going to shuffle it into a random order. So 7, 5, 1, 3, 4, 2, 6. Is that all the numbers? I don't know. I might be missing one. Oh, 0 needs to fit. All right, so we're going to still start with 0. And then you can say, all right, now based on those 8, I'm just going to take the first 5. This will be my training data, and this will be my test data.
Okay.
2 conceptually different ways, but they're essentially equivalent. Yeah? Thanks. Yeah?
Is there kind of a general rule for the optimal number of points you should include within your training data set? Or
Whatever works. I mean, for our purposes, yes, there's theory that will describe how well a machine can be trained and how many data points you need. But I can't give you that theory. I don't think we need it for this class. Because to be honest, with the handwriting or even the digits data set or something, my own handwriting, I found that I trained, I think that's your assignment today. It's writing a program that recognizes your handwriting. If I give it like one, even just one of each letter, for at least for up to like 7 or 8 letters or something, it only needed to train on one. It could draw the hyperplanes because I had enough dimensions that it was easy and they were easy to separate. So, but if you're dealing with something that's harder to figure out, and there's a lot of examples out there that are much harder to classify, then yeah.
You said you were looking for examples earlier?
Examples of unsupervised learning.
Okay, could you do something like with IRS tax data when they're trying to find like who's fake and they could just like put all the data in and see based on probability if someone's faking their data?
Yeah.
They do it with tracking your credit card also to try and find an anomaly in your spending.
Okay.
They'll just basically, they don't know what characteristics they need, and so they just let it learn off of how your spending goes, and when an anomaly is detected.
So yeah, that's called novelty detection. Yeah, and that could be unsupervised. Like, okay, good ideas. Yeah. Thanks.
But in that case, if you're like, at first you have no idea about the fraud, but after a while you can,
Yeah.
it becomes a supervisor.
Yeah, you know what the norm is, and then potentially, you see what fraud looks like, and then you can supervise it, yeah.
Any problem only starts with
Yeah,
these people, like, they.
right, because they start, the initial spending habits, you don't know what they're gonna be, what the norm is.
I think there might be something similar to authorship maybe.
What?
Authorship, seeing if it's like.
Authorship?
written by somebody.
Oh, yeah, to see if it's written, but authors, I mean, if you're detecting,
But if you're looking at like word styles, too, like what the verse is and like.
yeah, but some of that can be supervised, right? If you're trying to determine, like, you know this was written by Agatha Christie, you know this was written by Iris Murdoch, you know this was written by blah, 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 then you could train off those and then test on other stuff. So, but, yeah, so there are lots of good examples of classification. I don't have them off the top of my head. Yeah.
Also for the Yellow dot prediction, you said to know how slicing is necessarily good. So the data and then in brackets and
Yeah. Yeah, there was an interesting thing, I guess, and this didn't, the first time I took the class, this wasn't the case. But now, if you provide, was it test data or training data? Predict. So you're providing, using the test data and you're passing it in, you are not allowed to pass in a 1D array. You're not allowed to say, pass in a single one of these rows as test data as a 1D array. It has to be a two-dimensional array, but it can be 1 by n features. But it still has to be a two-dimensional array. So that's unusual. It doesn't let, so that means that you can't use a certain kind of slicing that you might have done before. If you have this matrix, and they usually call it, well, I guess that's all the data, we'll call it X, and you wanted to select a single row out of it, you might usually select that single row by saying the index of the row, all the columns, right? That makes sense? But this turns it into a one-dimensional thing. This results in a 1D NumPy array. So there was a simple trick, I think. I actually don't even remember the syntax. What was it to make that a two-dimensional?
It was just to be.
-1:? Ah, so 2:, for instance. -1:, was the last element. This is row 2, colon. I don't, to be honest, even know. I'm trying to think what that means. I mean, a single colon means, yeah, but that's, it's not from row 2 all the way to the end. I mean, I think, yeah, everything on the second, so I don't, honestly don't, it doesn't make sense to me.
It was in the documentation that if you pass in a lower dimension, then it assumes that you have, if you do this, if you do that, and then comma, colon, you get the same thing as 2 colon. So if you do 2 colon, comma, colon, you get the same thing as 2 colon, and it just assumes that you want the rest.
Well, 2 colon.
No. Yeah, there you go.
2 colon, comma, colon, that means everything starting at 2, rest of the rows, all the columns.
Yeah, and you get the same thing, don't you? If you
That's not what I intended. I don't think that's what it does, though. I don't think that's what it's doing. If I confirm who has the computer in front of me, I put it in the spreadsheet, yeah. All right, I'll look into it a little bit further as to why that's the case. But that's the main point there, is you have to make sure that when you're predicting, you ask for a prediction for a two-dimensional data set. It can be one row, right? Just one particular observation, one particular sample that you're trying to classify. But you have to make sure that you give it a 2D array. 1 by number of features. Yeah.
I'm a little confused about what how the NumPy reshape with the -1 index works at the very end. It's saying that.
Yeah. That -1 is used when you reshape, and -1 means you know how. Okay, so let's say, yeah. So we've got a NumPy array that has 3 or 4 rows and 3 columns, say, okay? Clearly, we can take that data and we could reshape it to have 3 rows and 4 columns. It's the same number of points. So into the reshape function, we can say, if this is my array called A, I say A dot reshape. I want to turn it into 3 by -1. It knows how many elements A has, so it can infer how big that has to be. You have to have an extra set of parentheses. You might have to pass a tuple. I don't remember. Some functions work differently.
So what would happen if you,
You can specify 4, that's totally fine, because that's consistent. But if you were to say 3 by 5, it would say, no, you can't do that. There's not enough data points to do that. That doesn't make any sense. But because it knows the number of points, total, that it has to maintain, it say, all right, 3 times what equals 12.
okay.
Yeah, so, with this example, like, maybe a whole different job, but it's unlike the flower where it doesn't have features, like in the whole thing.
He's asking how is the image classified? He doesn't have features like sepal length, and of course it's the only one I remember. I don't know, iris width. I don't know what they were. It does. It's got how many features? What was 64 with an 8 by 8 image? It's got each pixel. What's intensity of each pixel? Yeah, it works.
Could you overlook the examples of the individuals and steps? So, like,
Oh, yeah.
Like what are the steps themselves individual features, or are they actually the steps in one feature?
So I said, how about I give another example? Would that help?
I prefer to see
Okay. Pay attention. Okay, so this, the example was, you want to determine who's carrying a particular cell phone, right? So it's taking acceleration measurements as you're walking, and as you walk, it tracks your acceleration. And each person's gait is slightly different. They move a little bit differently, and so presumably the signal that this thing gets as far as the acceleration goes is going to be a little different for each person. And so I said that it picks out, we take 10 different people, right? And they each carry the cell phone, and they each walk 100 times, or for 100 steps, okay? Each person walks 100 steps with a cell phone. And then so I don't know, the step data might look like this. I'm gonna imagine it looks like a heartbeat, right? And so each one of these is a step. Okay? And so we've got 100 of these, and for 10 different people. And we cut them up, and we say we're going to take a look at the maximum acceleration amplitude. This is one feature. And we also look at the step time. I think that's what it was, the step duration. Is that right? So these are our features. These are the dimensions that we're going to classify according to. Does that answer the first part of the question? Does that make sense why that's the case? What we're calling features? If we were, then let's go a little further with this. We have 100 of these for each person, and we've got 10 different people, and that's the sum of all our data. So we're going to have 10 times 100 different rows, and we're going to have 2 columns. And that's the amount of data that we have. We're going to pick a subset of that to be used as our training data, a certain subset of those rows, either by doing a random permutation and then taking the first n and training with that and reserve the rest as our test data. And that's just checking to see if we trained our machine appropriately.
So each step would be a sample, right?
Yep.
Each step would have like 62.
Yep.
Would that be a 2D array?
So yeah, in this case, it's always our data that we pass in is always 2-dimensional.
Okay.
The array that we pass in is always 2-dimensional, even though we're classifying in a larger dimensional space, right? The points themselves you can visualize are, in this case, we have only 2 dimensions. We only have 2 features, the maximum and the time. But let's say I looked at this in a different way. Maybe I could have done the fast Fourier transform and took a look at the different frequencies involved. And for each of those frequencies could have been a feature. That's a possibility as well. In which case, okay, so let's say I have 10 different frequencies. I just take 10 points and find 10 frequencies. Then I could plot it in 10-dimensional space. But I'd still pass it into scikit-learn as a two-dimensional array. Number of samples, number of features.
This would be a problem
Yep. The X vector, or the X array that we use to represent all the data, sure.
Why would in certain cases a large amount of training data or samples lead to a decrease in accuracy? I think you said there were some exceptions.
Did I say a larger number of samples or a larger number of features?
You said training data.
So if you, I think typically always having more training data, which means more samples, is better. But you need, if you have a lot of features, in order to fully train your machine, you're going to need more samples to get there. And so I think that one thing we noticed with this, I'm imagining that the numbers 0, 1, 2, etc. in your digits data set is just as easy of a problem as recognizing your own handwriting, A, B, C, etc. That's what your homework is going to be. And in your assignment, I have you use, I suggested a 5x5 array instead of an 8x8. And I found that it only takes maybe one sample of each of these to fully, to make your classifier work perfectly for all the test data. And so that's 25 features. Whereas when we have 64 features, what you might have noticed is that if you don't train it with most of the data, it's maybe only 70% accurate. And so it has a harder time because there's a lot of features and not enough data. It has a hard time predicting correctly. So if you have more features, that's great. You have to have enough data to back it up. That's a way to put it. Yeah.
I think you could have like some bad training data.
Also bad training data, yes. If you have some outliers that in a lot of them, that's no good, but
I think just one is a programmatic kind of aspect of your data. If you have like one data company that is an outlier that breaks the linear separability.
yeah.
Yeah, the whole thing.
He said breaks the linear separability. He's saying like what if you run into a problem? You know, in our case, we had two-dimensional data, and our groups were nicely split, easy to split, right? What if you have a few of the red things are over here, and a few of the green things are over here? Well, then you're in a messy situation. You can no longer use a straight line to separate the two groups. It's not possible. And so you can imagine maybe you can draw some curvy line, and that's when you get into like when it talks about the kernel trick and nonlinear kernels. Maybe you've got something where it's like, well, the red things look like this. Here's your red points. And your green ones look like out here. Well, now you can't use a straight line or a hyperplane, but you could separate these guys with some sort of curve thing. So find the curve thing. And so that's when you get into the nonlinear support vector machines. That's what those are all about. That just brought up a thought. You guys don't need to worry about what's going on under the hood. Yeah, to be honest, I guess on your homework, I only have you use nonlinear SVM just to show that, hey, the linear one, nonlinear, sometimes you think, oh, it's more general, it's better. But not in this case. It turned out the regular one is better, the linear one is better. I also was looking before class, and I found there was a nice chart. If you know what your problem is, there was a nice roadmap that says, you know, ask you a series of yes or no questions. Do you have more than 50 data points? If you say no, it's like get more data. If yes, try this. Is it a supervised or unsupervised? Go branch this way. So a decision tree to help you select which machine to use. And actually, if you're doing supervised classification, SVM linear was the first choice. And if that doesn't work, then it suggests you go to a nonlinear one. parameter for thermals. What other questions do you have? All right, I'll let you take the quiz then. Password is the name of the module, SK Learn. Tian, you asked a very good question. That's what the quiz is about. Password and end time is, I don't know what time is it now, 12:35? 12:36? Oh, I think it's 42 or something. Make sense? All right. Shall I let you work? All right, I'll let you work, and I'll answer questions coming around. Somebody wants. I'm gonna start here.
I have a question about, so I think we're about how do you solve the problem, the property problem? I want to,
Yeah, well, sorry, I didn't get back to you yet.
yeah, you said you were going to
Oh, I actually talked on the phone, right, somebody else asked that about it, but, basically, don't look, as far as, so the PIC starts out, so here's on screen, here's off screen. It starts out off the screen, right? So for that, while it's off screen, you have to look at everything.
in that case, we'll get something here other than that, right? And
Yes.
after that, it will kind of stay there, but there.
Oh, I see what you're saying. Okay, sorry, no, I guess, no, you need to find the right frame to start at, that's what you need. Find the right frame to start at.
Yeah,
Or
I
I can,
have to
yeah.
have this,
So start,
most of,
start the entire head within the frame. So if you take the first frame and exit it properly. And then start looking at a box around it. But of course, that box has to be bounded, it can't look outside the area. And so for that, you have to figure out an algorithm that selects the pixels around it of a certain size, but cut it off at the boundary if necessary. So you need to, yeah, no, it is, but it's pretty easy to think about the minimum of 0 and where the edges of the block is. And I think you only have to do that on the left and the right side, you don't have to worry about the top and the bottom. So it's not so bad. Okay, and then once it's in there though, but yeah, I think what I did was choose a box that is just, it's 3 times as wide as the feature itself. It makes it way faster. Yeah. It's going to be a bunch of, initially for most, the first half of the class, so everybody is together. So a bunch of short problems that on that material. Short problems. And then once you get to the application, the modules and stuff, it'll be 1 or 2 somewhat longer examples. And that's all for it. Because it was the rest of the code we prefer over multiple choice. And I guess you guys have done multiple choice the whole time, so. The particular, I'll give you access to particular links that you can go to review. But not your own code. I'll decide on whether I'm going to do handwritten paper or something. No, I think I said it specifically in the email already. Whenever it comes to memorization, I don't expect you to memorize any of that stuff. Like I make mistakes in class all the time, like on the specifics of how you call a function, like what the name of it is, but I can always find it. And I will give you the resources to find it. The only thing I'm trying to prevent you from doing is finding large portions of code that you can copy and paste to almost solve the problem. Right? And so, yeah, while that has a place in solving problems, like seeing how well you can hack together code, on an exam we don't have, like, in reality, you're going to end up with part, never. I don't think it's a good test of what you learned in this class to be able to talk. Yeah, for now, or you could, they all specify what you're allowed to look at. They all have links to the first page. That's what they say. And I think the second midterm said, look at everything from first, and everything that's included here in the final specifier.
Ultimately, you still need 50% of that.